Alright guys, welcome back. I'm here to do a video, and today I'm going to do a request. One of my viewers sent me a problem to work, and they asked me if I could work it for them, and I said sure. Well, when they sent it to me, I was like, whoa, this is not a high school chemistry problem. This is probably a college problem. So it needs to say, it's been a little while since I've done one of these, so I had to go look up some formulas, and I had to look up some values and everything. So I'm just being honest. I didn't recall this off the top of my head. I actually had to look up the formula and everything. So let's just go ahead and get started with this problem, okay? All right, here it says, what energy in kilojoules per mole do hydrogen atoms release when electrons in the fifth shell fall to the first? Okay, in this problem, since they're asking us about energy, the first thing I thought of was the energy of a photon. Okay, but after that I couldn't remember about the shells. I remember there was a formula that we used, but I couldn't remember what the name of that formula was called. So I had to look up that formula. Now the formula that we're going to be using, or equation, is going to be the Rydberg Equation. So let me go ahead and write that down, because you're going to need that, okay? So let me write his name down. This is the Rydberg. I guess I should say Rydberg Equation. Okay. Alright, the Rydberg Equation is the following. It's 1 over lambda, and that's basically the wavelength. 1 over lambda equals R. Now the R is the Rydberg Equation constant. Okay, so we'll need that. And then what we'll do is we'll take that constant and multiply it by the following. 1 over N. And this N is basically an energy level. Now this N, the first N, is your final energy level that it's going to rest in. So I'll put a little F there. Some equations will show maybe a 1 or a 2 there, or even an F like I've written here. Okay, but we need to make sure that we square this quantity. Okay, after that we're going to subtract basically the same thing. 1 over, this time another N, but this time it's going to be the initial. Okay, so I'll write a little I there for initial. Now we will also need to square this one as well. Okay, now this is all we need for the equation. Now this equation will help us in the end to calculate the wavelength. Even though they're wanting energy, okay, we need to first calculate the wavelength, and we're going to do that with Rydberg's equation. Okay, now we will need his constant, so let's write that over here. The Rydberg constant is the following. You may see different variations of this, but the constant is 1.0974 times 10 to the 7th. And the units on this is meters raised to the -1. So basically it's 1.0974 times 10 to the 7th, all over just meters. That's another way you could write it. Now in the problem, they told us that they had the fifth shell. Okay, so they're telling us that our N, because it says it is the first shell, it's first in the fifth shell and going to fall to the first shell, so that's the end result. So our initial, our Ni, is going to be 5. Okay, and our N final, where we're going to end up at, is in the first level. Okay, the first, so there's that, the 1. So let's go ahead and plug these into this equation. So this will give us 1 over lambda equals, now for R we're going to need Rydberg's constant. Okay, now this is what R is. Okay, so let's go ahead and plug that in. That's going to be 1 point. Now, like I said, you might see a shorter version of this. If you do, please use it if your professor has told you so, or your teacher has. So just make sure you use that. So that's 1.0974 times 10 to the 7th, and I'll keep up with my units. I'll be a good boy. m to the negative 1 times, here we go, this is where we got to be careful, 1 over, now what was our final? Well, we finally wanted to be in the first energy level, so we'll write a 1 squared here, okay, minus 1 over our final one, which we, our initial one, which initially we started in the 5th. Okay, we got to remember to square that as well. Alright, so now we can clean this up a little bit. So what we have here is 1 over lambda equals 1.0974 times 10 to the 7th m negative 1. Okay, and then brackets. Now 1 over 1 squared, well 1 squared is 1, so 1 over 1 is 1 minus 1 over, and 5 squared is 25. So once again, we'll clean this up a little bit more. I'm just trying to make sure I show all you guys and gals all the math, okay? So 1 over lambda, sorry for the poor penmanship, 1.0974 times 10 to the 7th m to the negative 1, and what we have here is 1 minus 1 over 25, so that's basically 25 over 25 minus 1 over 25, which is 24 over 25. Now we can use a calculator to go ahead and clean this up. If you wanted to use a calculator earlier, that would have been totally a-okay as well. So just letting you know. Okay, let me clear this out. Alright, we've got the following. We've got 1.0974 times 10 to the 7th times 24 divided by 25. Okay, and we should get the following. So let's go ahead and write that down. So we have 1 over lambda equals, oh, I need to get that calculator back up there. I need to tell the calculator to just stay on top, so let me do that real quick. Always visible in the workspace, or always on top. So we'll say always on top, that way it'll stay up there for me. Alright, so that gives us 1 over the wavelength, and we have 1.053504 times 10 to the 7th, and it's still m negative 1. Now, even though this may look like we have solved for the wavelength, we really have not. What we need to do is we need to multiply both sides by wavelength and then divide both sides by this 1.053504 times 10 to the 7th m to the negative 1. But it's a lot easier, instead of doing that, just flipping it. So basically go ahead and pretend like this is, since there's nothing here in a denominator, pretend that it's already over 1, and let's just flip everything. So when we do that, we get lambda by itself. Lambda equals 1.053504 times 10 to the negative, 1.053504 times 10 to the 7th m negative 1 will now be in our denominator. So that will give us 1 over that number. So 1.053504 times 10 to the 7th. Like I said, all I did was flip it over. Okay, over the 7th, and then the m negative 1 is down here. Now what we need to do is punch that into the calculator. Okay, so let's do that. Alright, so we have 1 divided by this number that we just got. If you don't want to retype it because you're possibly lazy like me, you can hit second, answer, and whatever the previous answer was, it will put it down there, and you can press enter. Now when I do that, I get my wavelength. That is my actual wavelength. So let's go ahead and write that down. Alright, so our wavelength, I don't know if I've got any room left on this or not. Let me see. Alright, let me move it down. Yeah, I got just enough room maybe. Alright, so our wavelength then is equal to 9.49 2, 1, 3, 2, 9, 2. Hopefully I got all those right. 9.492, 1, 3, 2, 9, 2. Yes. Times 10 to the negative 8th. Oh, yeah. And then this time, this will become meters. Now, yay! This is our wavelength, which they didn't even ask us to calculate. But yes, we had to get this just so we can continue working on the problem. Okay, so we finally have our wavelengths calculated. Now you're probably wondering, why are you going so far out on your decimals? Well, I'm going so far out on my decimals because really, if you look back at the original problem on number 1 here, they did not tell us the number of sig figs. They did not give us a number. So what I usually do is I usually carry all the numbers until the very end in this situation. Okay, that's why you're seeing 9.49213292 times 10 to the negative 8th meters. Now, I didn't even bother to pretty up the units and convert it to nanometers or anything like that because the problem didn't ask me for that, and there's really not a need in doing it. The only time you ever convert units into specific sets of prefixed units is to show off or to make someone else happy. Okay, meters is the base unit of length. It's good enough. Okay, and you always want to make sure you always go back to the base unit when you can. Okay, so we're at wavelength here. So now we got to continue on to the second part of this problem. I know it's not going to be short, and I apologize for that. There's really no quick way to do this, okay, and make it make sense. Okay, so let's go ahead and continue on. Now what we're going to need to do is we're going to need to use two equations you're probably already familiar with. We're going to have to use the speed of light equation. All right, so let me go ahead and write that down. Okay, we're going to be using the speed of light equation, which is basically, what is that? Well, energy equals mcr squared. No. What is that one? Oh, yeah. It's C. Sorry, I was thinking of physics classes. All right, so the speed of light equation is the speed of light equals our wavelength times our frequency. Okay, well, I know you're probably saying, well, we know the constant for the speed of light, which is great. We're going to need that. But the problem does not even mention in number 1 anything about frequency. And you're right. But that's where we're going to use the second equation. Okay, we're going to also use the equation of calculating the energy of a single photon, and we'll be using Planck's constant with that. Okay, so let's go ahead and look at this. Now, let's look at that equation. Okay, for a single photon, the energy of a single photon, is energy equals H times V. Now, we're going to need Planck's constant, so let's go ahead and make note of that. And we're going to need the speed of light. The speed of light. Now, I'm going to use 3.0 times 10 to the 8th meters per second. Now, that's what I use in my class. Okay, on my reference sheet that I give my students, that's the speed of light that we use. Now, you may have a different value. You may have something like 2.9979248 times 10 to the 8th meters per second. If you have a different value for the speed of light, please use it in your professor's or teacher's class, okay? But in my class, we use 3.00 times 10 to the 8th meters per second. I know it's rounded, but it's fine, okay? 3 sig figs. All right, now we're also going to use Planck's constant. For that, we're going to have H equals 6.626 times 10 to the negative 34th joules times a second. Now, Planck's constant is another one of those that may vary slightly from publisher to publisher and teacher to teacher and professor to professor. You may see 6.63, you may see 6.626. I like using 6.626 times 10 to the negative 34th. Okay, so yeah, that's what we're going to use in my class. So, in this video, that's what I'm going to use. Alright, so we need to somehow manipulate this equation for the energy of a photon equaling h times v. We need to manipulate this, okay? And what we're going to do is we're going to solve this equation here for frequency, the v, and we're going to substitute that in for v, okay? So let's go ahead and take care of that. So we're going to get the v by itself on the speed of light. Okay, the speed of light then would be the speed of light divided by wavelength. Okay, so that's what we're going to substitute into Planck's equation. So this is going to substitute right in place of v. Okay, so here we go. So we have energy equals Planck's constant, which we will now need. Well, actually, let me go ahead and show how this is substituted in. There's the h. E equals h times v, but in place of v, we're going to write the speed of light divided by wavelength. Yay! Okay, now let's go ahead and plug in these numbers. Okay, energy equals, now Planck's constant was 6.626 times 10 to the negative 34th. Now this is going to be joules times a second. Let me go ahead and write that in there. Joules times a second. Now we're going to need the speed of light. Speed of light is 3. I might actually need to make my parentheses a little bit bigger. Okay, the speed of light is 3.00 times 10 to the 8th meters per second divided by my wavelength. Now my wavelength I got all the way down there a while ago, so let's get that in there. 9.492 times 10. I'm squeezing it in best I can, folks. Times 10 to the negative 8th meters. Alright, so we finally got all that in there, so let's go ahead and get this now. Alright, I'm going to punch this into the handy dandy cheat later and calculate this. Now remember, when I'm doing this calculation, this is actually for a single photon, what I'm doing right now. Okay, a single photon. Okay, alright, so let's punch this in. Okay, sorry, I was getting excited. Alright, we've got 6.626 times 10 to the negative 34th, so negative 34. There's Planck's constant times our speed of light, that'd be times 3 times 10 to the 8th. Yes, I didn't bother to put 3.00, that's okay. Then I'm going to divide it by 9.49213292. Yes, times 10 to the negative 8. Alright, so I'm going to make sure to close my parentheses. No, I didn't even open any, did I? I probably won't need any there. No, I won't. Alright, press enter. Alright, so finally I get that beautiful, beautiful number, that 2.09. Now you need to remember that that is how much energy it is for a single photon, okay? That's just for one, okay? So let's go ahead and write that down, okay? So that's an energy of a photon, which is, let me write it down, 2.09415525 times 10 to the negative 18th. Now, you're probably wondering about units. Well, in our units, since this is energy, our energy units is going to be in joules. Okay. Now, it's probably easy for you to see that because the seconds will cancel with the seconds, the meters which cancels with the meters. Okay, but that's how we get that. Now, if you don't know joules units, it's like meter squared times, I believe it's kilograms over second squared. Okay, but anyway, that's that. But this is how much energy it is for a single photon. Now, go back up there. What do they want the units to be in? That's what we got to make sure of. They said they wanted it to be in kilojoules per mole. Wow. So we got to do some more conversions, because the way that this is written right now is this is in joules per photon, okay? A single photon, okay? So we've got to fix that. So let's go ahead and do that. We'll do that down here. We'll do another conversion step. So that's 2.09415525 times 10 to the negative 18 joules. Now remember, this is for a single photon, so this is per photon, and I've got to fix that because I need this to be not just for one photon but in a mole of photons, so I need to convert that. Okay, so let me go ahead and take care of the photons. Well, there are 6.02 times 10 to the 23rd particles, tiny things like atoms and ions. Well, I'm trying to get this into moles, so there are 6.02 times 10 to the 23rd, yes, that's a 3, to the 23rd. Man, I really need to make that 23 better. Sorry. Make the 23 better. 6.02 times 10 to the 23rd photons in 1 mole. Okay, so now I can write 1 mole here. Now I need to convert joules into kilojoules. Well, there are 1,000 joules, because I need the J down here to cancel out. There are 1,000 joules in 1 kilojoule. So now this will finally give me my units of moles per joules, because check this out. Photon will cancel with photons, that leaving me with a mole, and then joules will cancel with joules, leaving me with kilojoules. Okay, so let's go ahead and put that into our handy dandy cheetalator. Okay, we have 2.09415525. Oh wow, this is a long problem, I told you. Times 6.02 times 10 to the 23rd times 1, which is not necessary, divided by 1, not necessary, divided by 1, not necessary, but divided by 1,000, totally necessary, divided by 1,000. And that finally gives me that number right there. That doesn't look right because that's a negative 18 and that's a 23. I must have typed it in wrong. Let's type it in again. I think I forgot my exponent. So 2.09415525 times 10. Oh, I did. Times 10 to the negative 18 times 6.02 times 10. There we go. Times 10 to the 23rd divided by 1,000. Now, just in case if you're new to this, it's numerator times numerator times numerator divided by denominator divided by denominator divided by denominator, and you can do that and you can get it right when you use dimensional analysis. Okay, so finally we get our answer. Our answer is going to be the following: 1.260681461, and that E means times 10 to the third, and our units now is finally going to be kilojoules per mole. Now this is way too many sig figs. I know in number 1 they did not request the number of sig figs, but myself personally, I always prefer 3 sig figs. So to try to help finally lighten this up a little bit, I'm going to write 1.26 times 10 to the third, because 3 sig figs is usually ideal, at least to me it is. Kilojoules, wow, that K is really big, I'm sorry. Kilojoules per mole. Okay, so finally there is our answer to number 1 for our request. And like I said, I'm sorry that I was long-winded in this explanation, and I'm sorry that it took so long to get this one done, but this was definitely not an easy problem. Okay, I could understand why somebody would want this worked out. Hopefully I did not make any mistakes at all in this problem. So please, if you need to pause the video, please pause it now, because now I need to work problem number 2. Like I said, I'm sorry that I was so long-winded. I really couldn't go any faster without really explaining it. So apologies. So please forgive me. All right, guys. I hope this was helpful on number 1. So if we're ready, I'm ready to go on to number 2. I hope everyone else is ready. All right. So yes, but that's going to be our answer. So now to basically move on to the next one, I need to clear this off so we can actually look at the next one that we're going to do. So all right. So I'm going to get rid of all this. Alright, so let's do that now. Alright, grab my little toolbox here and let's delete some of this out. Which, I'm so sad that I got to delete this because this was a lot of work. So, anyway, let me clear my screen off. Hopefully I've gotten most of it. And I'm sorry if that is bothering some people that I just deleted all that. And if it hurts anybody's feelings, I'm sorry. It hurt mine. And I'm the one that did all that work. But, yeah. Anyway, alright, so that cleared that out, which is good. Now, on this next problem, I'll be honest, I wasn't quite sure if I was going to be right on this or not. Because, like I said, it's been a long time for me, so my apologies if I ever do anything wrong. I never try to mislead anyone, but, you know, it has been a while for me on problems like these, so just being honest. But I'm here to help the best I can, so let's go ahead and look at this number 2, okay? On number 2, it says, what wavelength in nanometers? Alright, so they're already trying to see if we can show out by asking us to convert to nanometers. But anyway, what wavelength in nanometers would be emitted by an electron traveling at 67% the speed of light in a vacuum? And then they tell us the mass of the electron should be around 9.1 times 10 to the negative 31 kilograms. Now, when the problem was originally sent to me, the user, or the viewer, you can say, sent me it being raised to the negative 28 kilograms. And I thought that was wrong, but I looked it up just to make sure, and they usually use maybe 9.11 times 10 raised to the negative 31 for the kilogram. So I think that was probably just a typo mistake from the publisher. I'm just saying it probably was. So let's go ahead and look at this problem. This one, probably not as bad as the one that we did, but if you don't know the equation to use to solve this, it is hard. Now, I'm just assuming that what they wanted the student to do is basically use the Debroglie equation. If you don't know that equation, I understand. I honestly didn't remember it either. As far as doing it in a calculation, I had to go and look it up. And because we normally don't use the Debroglie equation in my high school chemistry class, we'll talk about Debroglie, but we will not do the calculations. But anyway, let's go ahead and look at this. So here, in order to calculate the wavelength of this electron, basically in nanometers, we're going to need the Debroglie equation. And let me go ahead and give that to you. Okay. Basically, the Debroglie equation is, whoops, I need to change the color of that. The Debroglie equation is basically the wavelength is equal to Planck's constant divided by the mass times the velocity, and the mass being the mass of the subatomic particle that we're talking about, which in this case is the electron. And the velocity is, of course, the speed of light, but at 67%. So far we don't have anything too unusual to do here, but there are some things that we would definitely want to make sure that we know when we're doing this, and that's definitely knowing where and how our units are constructed and derived from the equation, and I'll make sure to go over that. Okay. Alright, so the wavelength. Let's go ahead and calculate this. We need Planck's constant, which you guys and gals know now that I like 6.626 times 10 to the negative 34th joules times a second divided by, now I need the mass. The mass was, in this case, 9.1. That's what was given to us. Now this does tell us our number of sig figs. The number of sig figs is 2, okay, the 9.1. Now if they would have gave us 9.11, we'd have 3 sig figs, but we've only got 2 sig figs. Alright, so we got 9.1 times 10 to the negative 31, and this is in kilograms. Okay, that is our mass. Now we need our velocity. They said it was at 67% the speed of light. Well, if you remember earlier, our speed of light that I like to use is 3.00. Now you're probably already yelling, whoa, 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 stop, stop, stop. That's the speed of light. That's not 67 the speed of light. And you're right, it's not. That's exactly the speed of light. But what I'm going to do, just to make it easier on myself, I'm going to write down the speed of light. And to show that it's going to be 67% of the speed of light, inside here in these parentheses, I'm going to show that I'm going to multiply it. Okay, you know, if you want to draw a dot there, you can, a little asterisk or whatever. But, you know, put you a dot there to show that you're going to multiply it. And I'm going to multiply this by 67%. Now, all I'm going to do is convert it to a decimal and write 0.67. Then I'm going to close my parentheses. Now, what that will do is that will take care of the 67% of this. Okay, so all I've got to do now is just punch this into the handy dandy cheatulator, and this will, beyond a shadow of a doubt, give me my wavelength. Alright, so let's go ahead and take care of that. So we'll pull up our calculator and we'll punch this in. Alright, so here we go. Clear this out. We've got 6.626 times 10 to the negative 34th. Okay, there's that. Divided by 9.1. That's all they gave us. 9.1 times 10 to the negative 31. Okay. Oh, I might want to use a set of parentheses on my denominator since I got multiple denominators. So second insert. Let me put my parentheses in. There we go. Parentheses. 9.1 times 10 to the negative 31 times 3.00 times 10 to the 8th. That's the speed of light. But remember, I only need 67% of that. So that's going to be multiplied by 0.67, or you could just type in 0.67. Either one is fine. Please be sure to close your parentheses there, okay? Now, I'm having to do that because, see, I've got multiple denominators here. I've got 3 numbers in the denominator. So I made sure to capture, if you look here on the calculator, I made sure to capture all of my numbers in parentheses in my denominator, okay? All right. So there's that. That's how you enter that into the calculator. Now I'm going to press enter. Now this will give me the following. This will give me 3.622546661 e negative 12. So let's write that down. All right. So let's write that. That's going to give me 3.622546661 times 10 to the negative 12th. Now, I need my units for my wavelength, and my units of my wavelength, if you look here, is actually for length of the wavelength is going to be in meters. Now, that's not what they asked for. They asked it to be in nanometers. Now, let me prove to you that this is correct as far as the units go for the wavelength. Okay, that's the base unit of wavelength. But let me prove this to you. Okay, look at these units. You got to remember that a joule is basically this. A joule is, as far as the units, like if you were to break it apart, is really a meter squared times a kilogram over a second squared. Okay, and that's what we have there. But notice that Planck's constant is a joules times a second. So what you really have then is, since this is basically a joule, so let me mark this out so we can concentrate. Look at this. If this is really a joule and this is a joule times a second, you'll have joules times a second all over, And look at our denominator. Our denominator is made up of a kilogram. It's also, in our denominator, made up of meters per second. Meters per a second. Well, if you look at this, we have kilograms canceling out kilograms. We have this second canceling out this second, one of the two, and then this second is going to cancel out that second again, and one of these meters is going to cancel out one of these meters, leaving us with nothing but meters. Okay, that's how that proves that that is our wavelength unit here. So that also lets us know that we set this up correctly. Now, the only thing that we need to take care business of wise is cleaning up the correct units. Okay, we've got meters here. They said they wanted nanometers, so let's go ahead and fix that. So we will take this big long number, this 3.62254661 times 10 to the negative 12 meters, and we're going to put that over 1, and we're going to convert that. Okay, now down in the bottom we're going to have meters, and somewhere up on top we're going to need nanometers. Well, which of these is bigger? Is a meter bigger or is a nanometer bigger? Well, if you said meter is bigger, you're right. Well, how much bigger is a meter? Well, since the meter is larger, that means it takes a whole lot of these smaller ones to make this meter. It actually takes 1 times 10 to the 9th, okay, nanometers to make just 1 meter. And we need to punch that into our calculator. Or if you want to just swing the decimal and all that stuff yourself, you can. So I need to take this number, this 3.62254661 times 10 to the negative 12, and basically multiply it by 1 times 10. Let me go ahead and type that. 1 times 10. Well, I'll do the second E thing here. To the 9th. And because I'm only dividing by 1, so I wouldn't change anything. So that gives me that answer. So that answer is what I'm going to write down. Now, looking back, they only gave me 2 sig figs. Notice here, they only gave me 2 sig figs, so I'm only going to give them 2 sig figs. So my final answer is going to be 3.6 times 10 to the negative 3rd, and they wanted it in nanometers, so that'd be nanometers right there. Okay, that'll be my answer. Now, if you don't want to put it in scientific notation and you want to look at it in standard notation, you can go into the mode of the calculator, change it back to normal, and if it's not too crazy of a number, the calculator itself will go ahead and give you that number in standard notation and everything. I didn't mean to do that like I did, but let me see. The 3 point, yeah, let's retype that. That doesn't even look good. All right, let me clear this out. So we have, I'll show you that it will actually give us what we want. Whoops, wrong one. And one more time. I like hitting second enter. It saves you some time. Alright, so there's that. Press enter. Now we need this converted into basically nanometers. So there's that. Hit second enter one more time. There it is. So we're going to multiply that by 1 times 10 to the 9th. And we'll get that. So either one of those is fine. 0.0036 nanometers. So any way that you would want to write that between these two would be fine. At least I would be fine when you're writing that way, and I would assume that your teacher professor would be as well. So, all right, guys. I hope that me spending the time working out these 2 problems were helpful. I'm hoping so. So anyway, guys, I hope it was helpful, and if you need anything else, just shoot me a message and I'll do my best to try to help you guys. Alright, guys, y'all have a good one.